Hello everyone. Today we'll be going over voting paradoxes and how they relate to linear algebra. So for some background information, I'd like to go over what exactly the voting paradox is and where it originated before we get into the mathematics. So the voting paradox, also known as the Condorcet paradox, was created in the late 18th century and talks about how while collective preferences can be cyclical, even if the preferences of an individual voters are not cyclical. This is a paradox because while one thing may be true, another larger idea is false, therefore contradicting each other and creating a paradox. So, as you can see here in this graph, uh, while the opinions of A, B, and C are all connected, they might not make sense in direct relations with one another, as this graph shows right here. So, going back to the textbook. The textbook begins by giving us an example of preference order in an election. There are three parties, the Democrat, the Republican, and the third party. And so this column here shows the number of voters with this exact preference. Since the paradox is cyclical, we begin by creating a circle. And this circle has the three parties and the number of voters who would prefer them. So here we have 5 voters who would prefer a Democratic Party over the Republican Party, 7 voters who would prefer the third party over the Democratic Party, and 1 voter who would prefer the third party over the Republican. So given these voting tendencies, mathematicians can see which certain pairing running partners can end up with the final party of a Democrat, for example. So they can predict how the Democrat can be the overall winner by first asking for a vote between the Republican and the third, knowing that the Republican will win, and then having the Republican go against the Democrat, knowing the Democrat will win, given that 5 voters prefer the Democrat over the Republican. But with different manipulations, for example, by having the third party run against the Democrat in the first round of the election, they can have a different overall outcome because of the cyclical nature of the preferences. So, if we want to go and basically simplify how these relationships work, we can create a circle for each set of preference orders. So this preference order is the first one shown here, showing that this person prefers the Democrat over the Republican with the positive 1. This person prefers the Democrat over the third party because it's negative. If it was positive, we would know that the person chooses the third party over the Democrat, and that this person prefers the Republican over the third party with the 1 voter. We can see this here with Democrat, Republican, third. Okay, so if we want to combine these, we can have the constants in front and add up each of these circles with, so we know 5 voters prefer this circular preference order, and then we know going back up to here, 4 voters prefer this one, and so on and so forth. So how do we get this into linear algebra? We want to create basically we want to break this down into vectors because then we can manipulate them, we can sort of plot them, and we can figure out how to get more information with the data we're given. So we have 2 sets of vectors that we can get from this first set of data and the overall preferences we have here. We can have the third dimensional vector of 715 showing the preferences of 7 voters prefer third to Democrat and so on and so forth, or we can have the negative 1 1 of this voter showing this Democrats prefer to third, Republican prefer to third, and Democrat prefer to Republican. From this point, we want to create a basis for our data set so we can have something to go off of, and we need a basis for the subspace or else we won't be able to prove anything. So the textbook says we say that a vector is purely cyclical if it is in the subspace of R cubed. So that means we have to have this vector setup, K is all real numbers, so on and so forth. Second part, consider the set of vectors that are perpendicular to all the vectors in C. So we know that C perp contains this, all equals 0 because we're creating a basis here. And then since C1 plus C2 plus C3 has to equal to 0 for this to be true, we can create this basis that will help us prove future things based on the vectors we can get off of our Republican third-party Democratic example. So we are led to this basis for r cubed, given that this is 1, 1, 1. These have to be negative 1, 1, 0. It can be multiple other things, but this is the basis that the textbook has chosen. Okay, so now we want to represent the votes with respect to the basis, and then decompose them into cyclical part, acyclic part, and bring them back to a very simplified circle formulation. So we first know that we're going to the d is greater than r greater than t voter. So that was the vector that was negative 1, 1, 1. And we know here that we have the relationships between C1 plus C2 plus C3. So we know for the first part of the vector, we're going to have, as shown here, C1 minus C2 minus C3. And we get this because of the relationship C1 plus C2 plus C3 equals 0. But we know since the negative 1 is multiplied by the C2 here, we replace that with the negative sign. And same with the negative sign here with negative C3. And it equals negative 1 because that's the vector we're aiming for. For the second value, we have C1 plus C2 because of the positive 1 here, and plus 0 because of the 0 multiplied by C3 here, and that equals 1 as shown here and as shown here. And for finally the third data point, we have C1 as always plus 0 because C2 times 0 equals 0 obviously, plus C3 because it's multiplied by the constant 1. Okay, so now that we have our system of equations here, we want to sort of find values for these constants 1, 2, and 3 in order to make a very simplified circular formula as shown here. We have the textbook shows us the different steps that they take. So they want to first decide to get C3 by itself, figure out that it's 2/3, and from then you can plug it back in to the previous equations to get C1 equals 1/3, C2 equals 2/3, and C3 equals 2/3 as well. After finding this out, we can create a new equation or a new equality where the negative 1, 1, 1 vector equals 1/3 times this first section of the basis plus 2/3 times the second section of the basis plus 2/3 times the third section of the basis, in total giving us a 1/3, 1/3, 1/3 vector plus a negative 4/3, 2/3, 2/3 vector. If we want to transfer this into the cyclical portion, we already know what this looks like because this was explained back up here. So we have the negative 1, 1, 1 circle, but now we know it equals the 1/3, 1/3, 1/3 Democratic third party Republican circle plus the negative 4/3, 2/3, 2/3 Democratic third party Republican circle. So what is this information good for? Well, this information shows that since it fits into the basis, we know that these set of vectors are all perpendicular to the vectors in C. We know that it basically follows the rules, so we can now make assumptions off of it. And we know that we can compare it to other vectors of similar data sets. So if we were to flip the preference order of this voter to T is greater than R is greater than D, all we had to do is multiply this entire equation by negative 1 as shown here, and the same data would, the same proofs would hold true because it mathematically follows the basis. Now you may be wondering, why is creating these positive and negative mirror images or mirror equations of themselves worth it? Like, what's the point? So it goes into proving if something is a voting paradox. So here in this table, we have the positive spins of a voting preference. As you can see here, negative 1, 1, 1, negative 1, negative 1. So you can see that these are all opposites of each other. And so we now know that if we conduct an election as described, then after the cancellation of as many opposite pairs, remember these are opposite pairs, of voters as possible, there will remain 3 sets of preference lists. One from the first row, one from the second row, and one from the third row. These are the rows. But the catch is that there can only be a voting paradox if the ones remaining are all from the same sides. Remember, we need it to be cyclical. So if we had 2 positive spins and a negative spin, the circle would not be flowing, and therefore there would be no paradox. So, for the proof, assume that we have canceled opposite preference orders and are left with one set of preference lists from each of the 3 rows. Here we have the DTR circle, and we have the negative AA. So A here is an integer that is positive if the remaining lists are on the left, and negative if the lists are on the right, and 0 if the cancellation was perfect. Meaning 0 would be if no one preferred Democrats over third party, and the opposite is also true. So then the election is determined by this sum. Here we have each cyclical thing showing one preference order. And we end up, after adding all of them, we have the negative A plus B plus C, the A minus B plus C, and the A plus B minus C. And so because we need this to be cyclical, we need these mini equations all to be of the same sign, or else the circle will not work and we will not have a cyclical representation of how the voters feel of each candidate. So for example, we're letting the total cycle numbers be non-negative. The other case is similar. So if they're all greater than 0, the first 2 rows to see that C is greater than 0, and the first and the third rows for B is greater than 0, and the second and third rows together give A is greater than 0. So if the total cycle is non-negative, then each row, the preframing lists from the tables are left. That ends the proof. So basically what the textbook is saying is that in order for our paradox to exist, we need all of these to be the ones chosen, all of the positive spin, or all of the negative spin to be chosen, or else we'll have a ordering of preferences of candidates that will not be cyclical. While it still may be a valid ordering of candidates, it will not follow Condorcet's paradox and therefore cannot be used in our basis of 1, 1, 1, negative 1, 0, negative 0, 1. Okay, so let's do some example problems. Let's start with number 1. Here's a reasonable way in which a voter could have a cyclic preference. Suppose that this voter ranks each candidate on each of the 3 criteria. They want character, experience, policies. Alright, so let's create our table. So we have, sorry for my handwriting, I have a mouse, not a pen. We have the D, we have the R, we have the T, and we have character, experience, and policies. So we'll rank each candidate on how they fare against the other candidates for each one. So for example, let's have the Democrat have the most character, the second most experience, third best in policies. Republican, let's go 2, 3, 1, and 3, 1, 2. So purely by this is just basically a subset of the previous example the textbook used. And it's really easy if you want to compare to the cyclical format we had for Democrat, Republican, and third party. Since there's only 3 parties, we know that there's only 3 options, 1, 2, or 3, for how well each party can do based on each character trait of, or each criteria of character, experience, and policies. So if we start off with the basics of 1, 2, 3 for Democrats, we know that Republicans either have to be 2 or 3. So once we make them 2, and we can make these 3, the remaining one is 1. And then the third party right here just basically fills in the blanks to create a cyclical order for these character traits. The textbook then says, in this ranking, is a Democrat preferred to a Republican at least 2 out of 3 criteria? Yes, it's preferred in the character criteria, and it's also preferred in the experience. Is the Republican preferred to the third? Yes, it's preferred in the character and preferred in policies. Okay, we're gonna do one more practice problem. Let's do problem number 3. It mentions the political science class's mock election. I don't see that, but I'm just going to make up values that I know will work for the problem and sort of explain how this cancellation things works. So we're gonna have positive spin and negative spin votes. So we'll have the 3 different ways that it could work. So D greater than R greater than T. We have R greater than T greater than D. And we're going to have T greater than D greater than R. So with this one, we can have, let's say, 6 voters who believe in this, 7 voters who believe in this, 7 voters who believe in that. For the negative spin, obviously, it's just going to be the opposite, so I don't need to write out that. It's just going to be the opposite ordering. We can have 2 voters who believe in this, 4 voters who believe in this, 4 voters who believe in this. All right, now we want to do this cancellation of the opposite preference orders. So if 6 people believe in this and 2 people believe in the opposite, in reality, that just means that 4 people believe in this and no one believes in that. And so far we can do 4 people believe in this, no one believes in that. This one, I'm sorry, this wouldn't be 4, this would be 3. And same for this would be 3 people believe in this, no one believes in that. So now we have everything of the positive spin. And if we go back here, we remember this is what we were trying to prove here in order to be able to make it fit our basis and create a sort of system of equations from it. So if we want to create our own little circular equation, we know that 4 people believe in the circle of D is greater than T. This is ugly, I'm sorry, but downsides of having a mouse. Whereas T is greater than 1, and T is greater than Republican, and so far and so forth. Now we've added to the circle of 3 people believe in the DTR circle where this is 1. The negative 1 is located here. And the 1 is located here. Remember, the arrows go like that. Plus the 3 people who believe in this circle. Okay. Now that we have these circles, we can add this up to get our final circle, the one shown here, yeah, right here, of the total class's preferences. So we have this. Oh wait, this is the political science setting. This is good. We have new numbers here. This final circle would have a circle of Democrat, third party, Republican, obviously. So we would do the 4 times negative 1 plus 3 plus 3. So that would be 2 for this number. Then we have 4 minus 3 plus 3. So we'd have 4 here. And then 4 plus 3 minus 3. And then we'd have 4 again. So knowing this, we use our knowledge of cancellation and trying to get all non-negative or non-positive by cancellation to create one circle that could accurately describe the class's entire voting preferences. And we use different numbers than the ones shown in the example here, just so we could have some differences and test our knowledge to see if we really know it instead of using memorization of these numbers. Well, that's all for voting paradoxes. I hope you enjoyed this short presentation. I tried to keep it to the textbook in order to keep all my information as correct as possible. And if you have any questions, I'd love to answer them. Bye.